Does this seem reasonable? Exciting? No? No, not really? Okay. I'm tired. Y'all look tired. Feel tired. It's a long weekend? Yeah, I had a long weekend too. All right, I think we're ready. I think we're ready to set this integral up. Okay. So we're going to do double integral. Our limits of integration are going to be from 0 to 2 pi, 0 to root 2 over 2. Then I've got to do the f function minus the g function. Right? How could I rewrite this f function? Square root 1 minus r squared. We could do the same thing we did a second ago, right? We could rewrite this as square root of 1 minus parentheses x squared plus y squared, and that's r squared. We will want to get to a point where we can just look at that and see that this is root 1 minus r squared. Do you all see it right now? Okay. So that's my f function. That's the one on top. So I'm going to go root 1 minus r squared minus now the bottom function. And that's just r. Because x squared plus y squared is r squared. And then you take the square root. So this is just r. Right? That's the top minus the bottom. And then another r. Because we're doing polar. dr d theta. Distribute the r through. R goes in front of that root minus r squared dr d theta. And I think that's as far as I'm taking it. Let's talk briefly about the techniques of integration here. How would you do this one? You could do a basic U sub. Just use the integrand as your u, the derivative of that. You're almost there. You're off by constant. So that's just a basic U sub. And then this one's not worth talking about, right? Okay, and then you plug in, and you think you can take it from there? Yeah? Okay. Good. All right, this right here, we're not, yeah, I guess we are going to do an example of this right now. Okay, so remember what we did when we started chapter 12. We had a rectangular region in Cartesian, right? Then we did a type 1. A type 1 was your x's were between two constants and your y's were between two functions of x, right? This was type 1. Well, what if our theta is between two constants, but our radius is between two functions of theta, which would be kind of like this. It would look like this. Our thetas are between alpha and beta, but our radiuses, our radii, are actually changing. They're varying, and they vary as a function of theta. No, all that does is it forces our order of integration to go, just like we did here. Remember, when we did this, if this was from A to B, and this was from like G1 of x to G2 of x, what we're going to have here in that case, we call it H1 of theta and H2 of theta, is right there. I don't know if you can see that. So if your theta is between two constants and your radius is between two functions of theta, then your double integral becomes the integral from alpha to beta, and then h1 of theta to h2 of theta. This is all the same, but this order of integration can't change. It's got to stay this way. Still have the r in there. Now I'm going to illustrate this with a rather cool example, I think. I think a lot of things are cool that other people don't think is cool. So a sphere of radius 3 has a cylinder of radius 1 drilled out of it as shown below. Set up the double integral which yields the volume of the remaining solid. So we've got a sphere, radius 3. We've got a drill of radius 1, and we're going to drill out the sphere, the solid ball, and I want to know how much is left. What's the volume of what's left there? Yeah, so before I do it, so this is what you're thinking before I show you the picture. If we were to take a sphere and drill out a piece of it, right? So let's say we drill out like this. We just drill out this hole right here, right? Drill that out. Then you were saying what? It would be
The same as 5B on the take home, except now we're including that very small region on top and bottom of the cylinder.
Yeah, so you could find the volume of the cylinder, right? But then you would have this little cap part. We would have this little cap piece on the top and a little cap piece on the bottom. They would have volume to it. I think that's what you're saying. We need to figure that out, right? Yeah? Maybe? No, because my drill is not going through the center.
Oh, that's why.
Okay? I don't want to drill the center of the sphere. I want to go offset it.
That's actually really hard
To drill that? Yeah, no, that would be a difficult thing to create. But, all right, do y'all see the sphere? You see my drill? Drilled out that hole? So the way that this was drilled was that the drill bit was running tangent to the z-axis the whole time. All right? So you have the z-axis, right? And my drill bit came down the side of it. Instead of the z-axis going through the center of my drill bit, it was tangent to my drill bit. Understand the question? So I have some things here. I don't even remember what this is, but okay. So here's the sphere. Here's a cylinder. That's the cylinder. That's just a cylinder. That's my drill bit actually in the sphere, right? Now, if we just look at the part that got drilled out, where are those caps? Yeah, let's see. Yeah, you can kind of see it here. There's a little bit of a curve to the cap here, right? That's problematic. I mean, if it was a straight cut, you could probably figure out the volume of this just using basic geometry, but it's that little cap portion that's difficult. So let's just rewind everything here. If we're trying to find the volume of this, could you find the volume of the sphere without the hole, without the volume of this solid ball without anything drilled out?
Yes.
Yes. There's a formula for it, right? So what we want to do is we want to take the volume of the ball. I'll call it a ball because the sphere implies it's hollow. I'll say the volume of the ball, and we want to subtract the volume of the drilled part, right? This part is a check. There's a formula. Do you all know the formula for the volume of a sphere? 4/3 pi r cubed. Okay, so there's a formula for that. We would know it because we know the radius of the sphere. Okay, so that's a check. We just need to find this part right here. So, do we have a top surface here of the part that comes out? Do we have a top part? What's the top part? What's the surface that creates the top part of the part that gets drilled out? The sphere itself, right? Right? It was, what was it? X squared plus y squared equals 9 would be the equation of the sphere because it has a radius of 3, right? So we know that. Now, the bottom part would be this part, right? But that's also the sphere. That's a problem. So why don't we just look halfway and then double that answer, okay? So what would the top part be? You said it would be the sphere. And then what's the bottom part? The xy plane, right? Which is just z equals 0. So all we need to do is find the volume underneath the sphere, right? Just the volume underneath the sphere to the xy plane, but over what region, right? What's the region? And this is where things start to get a little complicated. That's right. This is why we have to have functions of theta. Okay, so let's try and draw just the ground. We had a cylinder, right? What was the radius of the cylinder? It was 1, right? That means the center of it would be here. So what I'm doing is this. I'm taking this three-dimensional picture. My drill bit came through here, right, like that. And then I have kind of like this weird cap-looking thing there. I'm going to take that and I'm going to double that volume, whatever that volume is. Understand? Now, the top of this, that top surface is z equals the square root of 9 minus x squared minus y squared. That's the equation of the sphere, radius, wait, was the radius 3? Yeah, so that's the equation, right? And then solved for z. That's my f of xy. The bottom, of course, is 0, so I'm not even going to take that into consideration. So I need to double this thing. All right. Let's talk about, is that a polar region? Is it a rectangular polar region? Is your theta between two constants?
Yes.
Is your radius fixed between two constants? It's not. The one way you could look at it is if you let your angle be here, right? Your radius is between 0 and whatever that distance is, right? But if your angle is, let's say, here, now your radius is between here and here. It's become shorter, right? Here to here, same thing. Change the angle, the radius changes. So the radius is a function of theta. So right now we have, maybe you can give me the restriction on theta though. What would the restriction on theta be? What would be the biggest it could be? Pi over 2 straight up. But what about to get this stuff down here? Negative pi over 2. Do y'all see how your angle, to draw this region, you got to go, your angle's got to be between pi over 2 and negative pi over 2. But you got to figure out how far to walk out. So I'm going to go negative pi over 2 to pi over 2. And these right here, h1 of theta and h2 of theta, I don't know yet. I'm about to get them. You're going to help me get them. So if you don't have anything else to go off of, let's go off of what we do know about that circle. Do you know anything about that circle other than that it has a radius of 1? I mean, anything that might be valuable to us in terms of trying to get it over to a polar. You know the equation of it. What's the equation of that circle? What's the equation of any circle centered at HK? Remember this? That's the equation of a circle that has a radius of r that's centered at HK. What's our center? 1, 0, right? So if we replace h with 1 and k with 0, then the equation of that circle is that, isn't it? That's the equation of that circle? Now, how could this be useful to us? Well, I would like to get this into polar, right? So why don't we just change our x's to r cosine thetas and our y's to r sine thetas and see what happens. You know what? Let's square that first before I do that. Okay, so that's the equation of the circle that we're looking at over there. Here's me expanding this, and now replace all x's with r cosine theta, all y's with r sine theta, and what will we have? This right here becomes r squared cosine squared theta, right? This becomes minus 2r cosine theta, then plus 1. And then this becomes plus r squared sine squared theta. Y'all still there? Equals r squared. I have an identity. Where is it?
R squared cosine.
R squared cosine theta and r squared sine theta. If you put those together, you could factor out the r squared. Right? If I put this next to this, factor the r squared out, I would get that, and cosine squared theta plus sine squared theta is 1. Yeah? So now what we have, well, 1, but then times r squared. Sorry. So these two together become just what? R squared. So I have r squared minus 2r cosine theta plus 1, right, equals r squared. So I still have the right side. Don't forget that. Now what can I do? Subtract r squared on both sides, and it's gone. It was right here when I expanded x minus y squared. When I expanded that, I got x squared minus 2x plus 1. So that 1 was from there. All right. Remember what we're looking for here. We would like r to somehow be a function of theta, which means solve this for r. Solve this for r, and what would you get? Let's see, 1 equals 2r cosine theta, right? Just move that to the right. Solve for r, divide both sides by 2 cosine theta. So what do you have? 1 over 2 cosine theta equals r. Another way of saying that is r is equal to 1/2 secant theta. No, because this was our equation. I moved this to the right, so it became a plus, and then divided through. Something doesn't seem right. Let's see. Let's try this. I'm going to leave it like this just for the sake of ease. If my radius, if my angle is 0, how far should I be able to walk out? Between 0 and 2, right? So what is cosine of 0? 1? Something's not right.
I think I know what it is. When we do the substitution for r squared on the right side,
I'm missing.
that's supposed to be 1.
What was the right side?
Uh,
What was the right side of the equation?
because we originally had x minus 1 squared plus y squared equals r squared, but you didn't substitute the r squared as the radius.
I had, the general equation. Oh, that's right. We had x minus 1 squared plus y squared. I had written the general equation up there, but I never plugged in what the radius of our circle was. What was the radius of our circle?
1.
It was 1, wasn't it? Remember when I was writing this? Right here. This should have been a 1. That's going to be a good thing. We need to back up. We need to back up. I knew something, I was like, secant theta, this is not right. I can tell that the radius is not doing that. Okay, so back up, apologize. Go to here, go back up to here. We're still going to have the Pythagorean identity, but replace that with 1. But that r squared is not going to cancel. Okay, cancel your 1s on both sides, right? So now you have these two with the Pythagorean identity. That and that become that. I still have minus 2r cosine theta, but then equals 0. This is it.
Would you factor out an R?
Now we factor out an r. So if I factor an r out, I get r minus 2 cosine theta equals 0. So you have two different solutions here. R is 0 or r equals 2 cosine theta. There we go. Sorry about that. When I wrote the general formula up there, I forgot to put the radius of the specific circle we were looking at, which was 1, into that. So, yeah. All right, so now let's see if this makes sense. This is saying that our radius is either 0 or 2 cosine theta, right?
Yeah.
So let's check this. If my angle theta is 0, what's r?
2.
It's 2, right? Cosine of 0 is 1 times 2. That would give me 2. So we would say walk between 0 and 2, right? What if theta is pi over 2?
0.
Cosine of pi over 2 is 0, right? So you're between 0 and 0. So this seems to be dictating how far out I walk. So our theta restriction should, or our r restriction should be what? 0 to 2 cosine theta. All right, I think I'm ready to set this up. The volume of the drilled part, right, will be equal to 2. Remember, we had to double it because we were doing just the top part. Integral from negative pi over 2 to pi over 2. Integral from 0 to 2 cosine theta. What are we integrating? The square root of 9 minus r squared. Was that all that we were integrating? That was it, right? Y'all know where I'm getting that from? That was the sphere solved for z. Now your r from your, this is the first time I'm not going to do it in red, r dr d theta. Okay. How would you do that? Basic U sub on this one again, because the derivative of it's out here. So let's do this one. I'm going to take this one the rest of the way because we haven't seen how to do this yet. So with time, I don't have enough time to start the next section. Let me see where I am on my notes here. Yeah, there's the homework. I'll leave that homework right there while I finish this out. All right, so I'm going to do this just on the side here. If I'm integrating 9 minus r squared r dr, this is my little scratch work on the side. Make a basic U substitution here. U will be 9 minus r squared. The derivative of that would be negative 2r dr. And this all depends on how you were taught how to do substitution. or how it makes sense to you. I try and get these parts to match. So I solve for it. I try and isolate RDR here. So I do -1/2 on both sides. So this integral, when I rewrite it, becomes what? -1/2 comes out, integral square root u, right? Because this is going to be square root of my substitution. So I'm going to write that u to the half du. And now do your integration. So -1/2 and then 2/3 here, u to the 3/2 here, plus some constant of integration. And that's just -1/3 u to the 3/2 plus c, but u was what? 9 minus r squared to the 3/2 plus some constant. So just the inner integral, if I were doing it just as its own little integral on the side, this is what it would be, right? Okay. So now I'll continue this. So the volume of the drilled out part would be equal to 2 integral -pi/2 to pi/2. And then the antiderivative of that, which we found to be -1/3, 9 minus r squared to the 3/2. And we're evaluating this from where to where?
0 to 2.
What is 0? R is 0, right? To r is what? 2 cosine theta. Got to figure out what all that is. And then the next part would be d theta. Well, this looks like it sucks, doesn't it? So do you remember what the instructions said? Set up, but do not evaluate?
Yeah.
Okay, we're about to see why the do not evaluate part's about to come in, all right? Because we're going to replace r with 2 cosine theta. And I think this is where we're going to get to a point where we're going to not know how to integrate. Let me pull this constant out. This will be -2/3. And then when I plug in 2 cosine theta right here, I'm going to get 9 minus 4 cosine squared theta. That's what happens when I square the r, right? Square that. Then all to the 3/2. And then minus, now plug in 0. That's good though. What happens when I plug in 0? It's get 9 to the 3/2. And then d theta. So this is the point at which we would say, no, right? This right here is not something that you can integrate easily.
Oh, you could.
Wouldn't you use that half?
Yeah, but then you're going to have raised to the 3/2, and how is that going to factor in? I think that's going to be the limit of what we can do by hand. Now, the reason I wanted to work it a little bit, I just wanted you to see how these go in when they're not numbers. Like these are functions. So this is what you get. Now in problems that I would give you out of the homework, they're going to be things you can integrate. All right? Are we curious to know the answer? Not really? No? I mean, we could go to like Wolfram Alpha and type it in, right? We could.
Is there not a way to do that by hand?
I don't see, I mean, we could integrate this by hand. That's fine. This is not. Remember what that means. That's actually 9 minus 4 cosine squared theta times the square root of 9 minus 4 cosine squared theta. And that's what it means to raise it to the 3/2. And if I were trying to integrate that, I mean, maybe there is. Maybe there's something we could do, but I mean, I'm looking at a long day right there. You know, that's a lot of work. Well, you know one way we could do it. No, we could go to a computer to get it, and then compare that answer to and look at it and say, could we have ever gotten to that? That's a lot of times that's a good indicator of whether or not you're capable of it. So I'm just going to do the integral. I'm going to make this a little bigger so we can see it. Nope, can't do that. I think I'm going to go with this. Okay, so the original lower bound was 0, and then it was 2 cosine. I'm going to use t instead of theta. And then the expression that we integrated originally, what was the original? It was square root of 9 minus r squared, but then we also had times r, right? And then dr d theta. It's still thinking. There we go. Okay, so yeah, we're not going to be able to do that by hand because it's using the elliptic error function. Oh, you can't see that, sorry. Yeah. So Wolfram alpha, in case you don't know, Wolfram alpha, the kernel, the brains behind Wolfram alpha is actually this program called Wolfram Mathematica. So if Mathematica can't do it, Wolfram alpha is not going to be able to do it because they're the same brain. Now, it's giving us an answer, but it's not something that we would be able to do mechanically by hand. Okay? Now, I wonder if we could get that answer, though, like that real answer. Didn't you want the answer, or no? Just to know. DDT. You know what a DDT is? It's an old wrestling move. Classic, yeah. I should have put a decimal. Hold on, I need to turn one of these into a decimal. Still going. Oh, there we go. Oh shit, it's got imaginary numbers in there. Yeah, but that's a problem with the computers. Computers having a little bit of an issue. This is essentially 0. Right, 10 to the negative 15. This is like an infinitesimally small number. This is basically a 0. So about 8.58. What was the volume of the sphere? It's 4/3 pi. Oh yeah, I didn't double it. So double. I'll have that do that while we're thinking here. 4/3 pi. What was the radius? 3. Wasn't it, of the sphere? Cubed. So 936 pi. 36 times pi. (113 minus 17.164-ish. I screwed that up. 113 minus 17. So this is the volume of the sphere. That's the volume of the part that got drilled out. So you'd have the volume. All right, let's sign in. Staying on top of this. Wait, everyone turned in their things, right? I'll still have you sign in, though. Unless I'm out of dates here. It's the 25th? 30th. It's like, wait a minute.
Even you said it was hard.
I know. I forgot already. There we go. All right, as soon as you sign in, you can go. Sorry to make you wait, but it's not even 12:40 yet.